encrypt the key using RSA, and then teach us the algorithm and the private key in class.
Awesome.
Problem solved.
Yay.
If you're not smart enough to figure out how to decrypt it, then good for you.
It'd be really bad in encrypted quizzes.
Oh, God.
Question 1, decrypt the quiz.
Honestly, I would love that.
Let's keep it in mind.
I just want to see at the top, so if begin the public quiz.
Yes.
Maybe I'll do that as a joke if I teach on April Fool's Day. Let me pass out a sign-in sheet.
You can put that in our email so that you can send us that password.
Yeah. Today is the 12th.
Yes. That'll work. This is so tiny compared to the 24.
Yes, question.
Yeah, in number 4, homework 3, it says, assuming that Goldbach's untitled is as opposed to number greater than 7, or greater than or equal to 7. I think it should be 9, because it doesn't go for 7.
You can't do 7 as a sum of 3 primes?
3 odd primes.
Doesn't have to be odd, does it?
Yeah, it says odd.
Oh, really?
If it's going to be odd, it's going to be greater than or equal to 9.
Alright, that's an edge case. Ignore the edginess. Is this homework 3 we're doing?
Yep.
Yes.
Where's my mouse, man? Yes, that should be greater than or equal to 9. Or it should just say 3 primes. I think I tried to make it easier by saying odd primes. So, odd numbers greater than or equal to 9 can be written as a sum of 3 odd primes. Let's do that one. Other questions on the homework? All right, working. So, I'm going to give you a quiz on Friday. Probably I'll give you the whole class period for it. And it will cover what we've done so far, but it won't cover what we do this week. So everything up to and including what's on that homework that you're working on right now, but not the stuff we're going to do today and the rest of the week. The bad news to the quiz is there's going to be an earthquake drill on Friday. I'm clairvoyant, I know these things. And it's at 10:15, so it's going to be right in the middle of class, which means that during your quiz, you're going to hear a drill you're going to have to drop and cover under the tables. But you can do so with your quiz and keep working quietly.
Isn't it on Thursday? Not on Friday.
Is it on Thursday?
Isn't it 10:15 and 10:15? That would make it Thursday.
All right. If that's the case, forget everything I just said.
Let me check, because I know it's a national thing.
Yeah. Thursday, you're right. Okay.
You got my hopes up.
Earthquake drill. Well, you can still do the quiz under the table if you want. Yeah. All right. So earthquake drill on Thursday. So basically, when you hear the alarm, you want to calmly and quickly drop down, get under something solid like a table, and just hang out there until we get the all clear. And it may feel goofy to do that sometimes, but it's a muscle memory thing. You want to kind of get in the habit of when you hear an earthquake alert, that's what you do. All right, but the quiz will still be on Friday.
So the drill's on Friday, Bill?
The drill is on Thursday. Yeah.
Your clairvoyance is flat.
My clairvoyance is a little out of tweak. All right, so other questions? finished by talking about modular exponentiation, I think, where we were looking at, did we do modular exponentiation? I don't think we did.
You might have been just touching on it at the very end.
I think that's what we left it with. So suppose we want to calculate something like 3 to the 17th modulo 7. And we have Fermat's little theorem. Which tells us this. A to the p minus 1 is always congruent to 1 modulo p, as long as a is not a multiple of p. But that doesn't really help us here. We could say 3 to the 6th is congruent to 1 modulo 7, and we could bump up. But if this number were really huge and weren't close to a multiple, thank you, of p minus 1, that wouldn't help us. But we can do something else here. We can take the number 17 and write it in binary. And so we can note that 3 to the 17th is congruent to 3 to the 16 plus 1. Because that's what 1, 0, 0, 0, 1 means. And we can always do this with powers of 2, which is congruent to 3 to the 16 times 3 to the 1st. How does this help us? Because finding 3 to a power of 2 is really easy. And we can do it as follows. And we're always going to be mod 7 for this exercise. 3 to the 1 is congruent to 1. No, it's not. 3 to the 1 is congruent to 3. So we know that automatically. If 3 to the 1 is congruent to 3, what is 3 to the 2 congruent to? Without doing any work or thinking. Too much work. How'd you get 2?
Well, 3 squared is 9.
It's 3 squared. 3 to the 2 is congruent to 3 squared. Right? Because we can square both sides of a congruence. And that we can say is equal to 9, which is congruent to 2. If 3 squared is congruent to 2, what is 3 to the 4th? What's it congruent to? How does 3 to the 4th relate to 3 to the 2?
Squared.
It's the square. 3 to the 4th is 3 squared squared. And we know 3 squared is 2, so this is 2 squared, which is 4. How does 3 to the 8th relate to 3 to the 4th? 3 to the 4th squared. And we know 3 to the 4th is 4, so this is 4 squared, which is 16, which is congruent to 2. So the things that we actually need to compute modulo 2 are small, 9, 16. And 3 to the 16th is 3 to the 8th squared. And 3 to the 8th is 2, so this is congruent to 2 squared, which is congruent to 4. Yes?
Why doesn't 3 to the 1 follow this pattern?
Oh, that's a deep question. Patterns in these things are fascinating. I don't know why 3 to the 1st doesn't follow this. Or even worse, why 3 to the 0 doesn't. Because 3 to the 0 would be 1. It's a good question, but I don't have a quick answer. I mean, I don't know any answer, so I think I have a slow one.
I was going to say something about 3 to the 1 is in the power of 2, so...
Well, we can't double 0 and get
Exactly.
1, so that sort of breaks. So maybe something like that.
Yeah.
I know that Wikipedia has an excellent explanation as to why it does not.
Oh, cool.
I can't remember what it says.
Okay,
So I
look
had
up
the same
Wikipedia.
question when I looked at Wikipedia.
Cool. I'll have to check that out.
Under modular exponentiation.
Yeah. So we have, with very little work, expressions for what each power of 2, power of 3 is congruent to modulo 7. And so now, given this, that we only have to do once, if we want to find 3 to the 17th, it's 3 to the 16th times 3 to the 1st. 3 to the 16th is 4, 3 to the 1st is 3. That's congruent to 12, which is congruent to 5. So 3 to the 17th is 5 more than a multiple of 7. And once you've done this once, if you wanted to find 3 to the 19th, that's 3 to the 16th plus 2 plus 1, which is 3 to the 16th times 3 to the 2 times 3 to the 1. And 3 to the 16th is 4, 3 to the 2 is 2, 3 to the 1 is 3, which is 8 times 3, which is 1 times 3, which is just 3. So very little work to do these high exponents. And if I raise this to a 12-bit number, right, something up to like 4,000, it would take at most 12 of these powers of 2 that we would multiply together and keep reducing modulo 7. And in general, to find 3 to the n is going to take us log base 2 operations, log base 2 of n. So we started talking about order efficiency. Did we? No, I'm confusing the courses. We'll talk about it later. But if n is 1,000,000, it's only going to take us 20 operations to find 3 to the n, as opposed to 1,000,000 by multiplying 3 by itself 1,000,000 times. So this is a really, really efficient way to do exponentiation. Yes?
I'm kind of confused as to what happened in between the congruency of 8 times 3 to the congruency of 1 times 3.
I said 8 is congruent to 1.
Oh, okay. Gotcha.
So I just reduced it on the way. Or I could have done 8 times 3 is 24, and then found 24 was congruent to 1. But if you're multiplying a bunch of things, as soon as you multiply 2 things and you're bigger than 7, you can reduce it. And then you're back to just multiplying small things by other things. When I was a kid, I was convinced I had a formula for generating primes. And I wrote to a mathematician, I think he was at the University of Illinois, and said, you know, I think I have a formula for generating primes, can you check it for me? And he wrote back, and it was actually a really nice letter, and told me that that number I generated wasn't prime, and that you could see it with a calculator. Calculators had just come out at the time. You could see it with a calculator, and he showed me how to do this kind of thing. And without having to do large computations, he took this number. Basically, I generated a number so big I couldn't test it. And I'm like, oh, it's got to be prime, you know. And he showed me how I could test it using this kind of approach, and that was pretty magical to like unravel. But the nice thing is you can teach a computer how to do this too, right? And we could have a computer just multiply 3 by itself 1,000,000 times, but it's going to take time. But you can teach it how to use modular exponentiation, and it takes 20 operations. And now you can start dealing with these really, really large exponents. And we're working towards this idea of Mercian primes, where p might be, you know, 100,000 digits itself. And so this is a number with several tens of thousands of digits, base 10. And you can't iterate that many times. There's not enough time in the universe.
There's a distributed computing project that means that.
Yeah, there's the Great Internet Mercian Prime Hunt, GIMP at Home, that uses these algorithms that we're, things like these algorithms that we're talking about.
They're up to like over 10 million digits long.
Yeah, the bar keeps rising.
Crazy.
You can actually find the prime expanded out online. largest known prime. Hey, it's the gun there. 17.4 million digits.
How can you even store that?
That's only 17 megabits, so 2 megabytes.
Oh, yeah, I did this math, that was 17 gigs per second.
2 megabytes for just one number.
Oh, I gotta clean the filter. So there's the largest known prime as of this month, to the 57,885,161, which means that this number itself has got to be prime. And that was discovered by Gim Punch.
They omitted, so 17 and a half million
Yeah, you
digits.
can find these online though.
I like this is the number, but we trimmed out, 99% of it just for the sake of brevity.
That's prime
Nothing
data.
big, it just happens to be the population department, nothing too major.
I thought they worked up to it.
Oh, come on, I know it's on here.
Eventually we'll find the
We'll do
actual
American
number.
style. There you
There
go.
we go.
Oh my god.
Wait, there's still a
Oh,
middle line.
sections. Just in case you get lost.
Oh my god!
Ah, ooh.
Because
It's 9.56
if it's
big.
that big, if it's that big, I mean, you don't want to send that thing right along. You want to make sure, really sure, that you want to download a number that big.
Alright, I'm downloading it.
When you
Put it in
download
my
it, then what are you going to
background or
open it in?
something.
Are you going to open it in Notepad? Because then it's probably going to crash.
And I'll just cat it from a Unix shell.
Oh,
Oh yeah, that'll work.
Make sure you use less.
Yeah. I actually found, I don't know where it is, but I actually found something that will print this out in English.
Well, I actually, if you go back one page, it actually has
It
it.
does say that on the right side.
it Yeah. into
a text-to-speech device.
English
Oh yeah,
name.
English names. Okay.
That looks like an efficient way to store that.
Octo.
Yeah.
Wow. Okay.
I didn't even know you could break
Trey,
numbers down
Milla,
like that.
Milla,
Yeah.
Yeah.
Septuagint,
This sounds like the dad from A Christmas Story swearing.
Yes. This would really trip up Big Bird with his alphabet song.
Can I get
That's all
points
the
for those
coolest
in
word.
Scrabble?
So yeah, primes are big, and there's no limit to them, right? We've already seen this. There's an infinite number of primes. And we can use them for useful things besides cool t-shirts. So let's talk about applications of all this stuff.
Like you put the first digit on the shirt and then you'd say like this many numbers omitted and then you put the last number on the shirt because that's all you'd have space for.
Or you get like 500 million of your closest friends and you each wear a digit.
Alright guys, line up in order.
Yeah, exactly.
I think you and you, no.
So applications. First application, parity. So here's the setup. We're transmitting information from one spot to another, say from a keyboard to a computer. And we're doing this old school, right? Go back to like the 60s, the 70s. We didn't have an internet. And you weren't allowed to hook a modem up to your phone line. It was illegal. Because AT&T had this draconian grip on telephones and telephone lines. Watershed ruling, they decided that, the courts finally decided that you were allowed to send information audibly over a phone in whatever way you wanted, and that was allowed. So you could have things like answering machines as long as they didn't physically connect to the copper in the wall. So this thing would detect when a ring came and it would listen to a message and it would speak a message and it would record it using just plain old audio technology. And so this allowed the creation of modems, ways that you could send digital information across a phone line. And it was done with a series of tones. You'd use a high tone for a 1 and a low tone for a 0, or vice versa. And by squeaking and squawking high and low in the right way, you could transmit these 1s and 0s, which means you could transmit characters, numbers, files, pictures, things like that. Okay, so these were acoustic couplers, and you know, AOL, if you remember the AOL days, you look at like AOL's, 24 back in AOL times and stuff. There's all these squeaking and squawking that you always hear when you establish a connection to a computer. And that worked fine, except that it was prone to errors. If your cat started shrieking at the dog in the background, you might get a transmission error. Because what you thought was sending out a 100101, well, at this point, your cat falls off the ledge and shrieks, and it sounds like a different tune, and this becomes a 1. Right? And so this was prone to errors in your transmission. So that's the ASCII code for the letter A. That's the ASCII code for the letter C. So I'm entering your final grades into the computer, and I'm typing in A, and as it gets sent to the other side, my cat freaks out, and you've got a C for the course. Right? So you need a way to detect this and be able to know that the information that was sent was corrupted somehow. And an easy scheme for that is to use what's called a parity bit. So here's the idea. Let's talk about odd parity. And there's odd and even parities. Let's talk about odd parity. The idea is you're going to add an extra digit to the end of this, such that the number of ones in that whole string is odd. So in this case, I would add a parity bit of 1 so that I have a total of 1, 2, 3. It's an odd number of digits. Now, if this is what I send, and this is what the computer receives, it counts and says 1, 2, 3, 4. That's an even number of ones. That's not supposed to happen. And it says, hey, there's an error in the transmission. Send that character again. And so my side would resend the A like this, and if it receives this, it says 1, 2, 3. That's an odd number of ones. That's a good bit. Good character. So it's an easy way to detect when one bit is flipped.
Wait, or one is flipped this one way, one is flipped the other way. I can't do that.
If 2 bits flip, you can't detect it.
Is this what like packet loss is?
Yeah. So if a single bit flips, you can always tell. And if the parity bit is the bit that's flipped, you'll also be able to tell. Because again, you've got an even number instead of an odd number.
And you're transmitting the amount of odd or evenness of it before that, correct?
Correct. You're transmitting the 8 bits of information, and then you're transmitting a 1 or a 0, so that from these 9 bits, you have an even or an odd number. In this case, an odd number.
Right.
So add an extra bit, which is called the parity bit.
So, but how does it know whether it's looking for odd or even?
It's established ahead of time.
Okay, that's what I meant. Yeah, that's the beginning of it. I remember this enough from my class getting in trouble.
And part of what you did when you wanted to connect to a computer was you had to decide, am I going to use odd parity or even parity, and they'd usually tell you what they were expecting. That's a good rudimentary error detection, but it's not very bulletproof, because if 2 bits get flipped, then you won't notice the difference. But it's a good first order. And this is nothing but add up the bits, figure out what it's equal to modulo 2, and if that's equal to 0, add a parity bit of 1. If it's equal to 1, it's already odd, add a parity bit of 0. So you just add up these 8 bits. See if it's even or odd. If it's even, parity bit should be a 1. If it's odd, parity bit can stay a 0.
It says I equals 0 and what's that?
7?
Oh.
Yeah. 8 bits. Or 1 to 8 if you like.
remember we had these in hyperterminal.
In what?
Hyperterminal.
Oh, yeah. Windows has a thing called hyperterminal that
I was using parity.
yeah. I suspect Putty may still.
It doesn't have hyperterminal anymore, they got rid of that.
Yeah.
Putty's about the only thing you can do for serial. But you can use it for
I'm not going to peek through here, but I'll bet you somewhere in Putty there's a way to
It's in
set up
serial.
parity. Yeah.
It's in serial. Even mark space.
Right, so it's still used, but most of the time we're not using acoustic devices anymore to send information. We're using an internet which has layers on top of layers of integrity checks and ways to restore packets. So most of our communication is pretty reliable now. But if you get like a little transceiver and hook it up to a PIC processor and try to send information from your laptop, you're back to where you might have an error-prone situation. Someone turns on a piece of equipment and you might change a 1 to a 0, and so parity can be useful. And there's other versions of this. There's a cyclic redundancy check, which I think is like a 15-bit code or something. It's a more complex process to generate this. You take a stream of input and you run it through a polynomial and you come up with something, but you reduce it modulo something else so that you get a constrained set of possible outputs. And it's another version of error checking. And if you have multiple errors, you can detect it with this. ECC is something we use in memory, error checking and correcting. You have 32 bits stored in your memory. You add 3 extra bits, which are these check bits. And I think ECC will detect if 2 bits are incorrect, and it can correct if only 1 bit is incorrect. It'll be able to tell which bit it is, and it can actually restore it. It's either 2 and 1 or 3 and 2. But it's used in memory systems, so that when a memory bit gets changed by a stray cosmic ray coming in and hitting it, the system can actually correct it and put it back to the right value. And parity just tells us there's a problem somewhere in this byte, right? ECC can actually tell us which bit has been upset, so that we can flip it back.
How is that possible to specify which bit it was?
Oh, it's a really clever algorithm that I haven't looked at in years. But yeah, it's definitely possible. And I'm sure Ricky has a good page on it. And they should talk about the algorithm. Worst case, if you have an 8-bit number, you could store the number twice. That's really expensive bit-wise, but that gives you a way to know if a bit is upset or if 3 bits are upset, but it doesn't tell you which bit was the correct value. In other words, if I have something like this, well, I know that something's wrong in this bit, but I don't know which one is correct. So you can actually store 3 copies and say, oh, that's a 1, that's a 1, that's a 0, this must be the bad copy. That's called triple modular redundancy.
But ECC doesn't.
But ECC doesn't do that. It's much slicker. It only uses 3 extra bits.
Keep in mind, this is literally downloading the same thing 3 times.
Yes.
Think about that for a second.
Very expensive.
Don't like planes have to use something like this? Like they have that redundant computers?
There are a lot of systems that use redundancy, and it was a really hot topic in the 80s. There were companies building fault-tolerant systems, and a lot of it was based on simple redundancy. And I've actually done some research myself on things related to that. And it's not as dorky as it sounds necessarily. Because you can use it tactically and just make certain pieces bulletproof and use those to fix other pieces. But that takes us away from number theory, so let's come back to number theoretic applications. So universal pricing codes. So here's my lunch. Right, so that's the number at the bottom, and it's got this. Right? And that's all that gets looked at when you pay for your item. If it rang up at $1 million, they would charge you $1 million for it. If it rang up for a penny, they'll charge you a penny for it. So this has got to be a reliable system. And what happens if you're very clever and good with a Sharpie and you take your bar and before you go to the checkout, you do this, and you change your Rolex watch into a Cliff Bar.
Chocolate Builder Bar.
Chocolate Builder Bar, and it rings up for, $2. And there's your Rolex. So this code has error checking built into it to make sure that what it reads is actually a valid number.
What are the actual numbers down there?
Let's see.
Like, did they mean anything?
For the first 6.
So this is the product category. I guess 7 means like artificial foods or something, I don't know. That's the product category itself. And then this is the manufacturer. So everything made by Cliff or maybe some parent company of Cliff. And then this is the actual item itself. So that's unique for each manufacturer. And then this is a check digit. And here's how the check digit works. So if we call this X1, X2 through X5, X6 through X11, so we compute 3 times.
Mr. Marcius?
Yes.
So it's for the manufacturer code.
Mm-hmm.
Are you sure it's X2 to X5? Because, well, there are 5 digits.
Thank you. Thank you. That would have tripped me up for like hours.
And of course, we're not using 0 index or anything, but that's just
Yeah, that's
implementation
just.
dependent.
So we take basically the odd positions, we add them together, and we multiply by 3. And then we add the even positions. And we reduce that modulo 10. And then if it's not equal to 0, subtract from 10. And that will give us our check digit. I'm afraid to try it because I haven't tried this ahead of time. But let's give it a shot. So 7 plus 2 plus 5 plus 6 plus 1 plus 2. So that's 3 times 23 plus, and then the even digits are 2 plus 2 plus 2 plus 0 plus 4, which is 10. So this is 69 plus 10, which is 79. Modulo 10, that's a 9. It's not equal to 10, so subtract it from 10. 10 minus 9 equals 1. There's your check digit. Now, if you work through the modular arithmetic, you can convince yourself that this will not only detect if one of these numbers is wrong, but it will catch a transposition of digits. Because we're multiplying odds by 3 and evens by 1, and it's probably because 3 and 10 are relatively prime, if you swap, say, x5 and x6 with each other, you're guaranteed to get a different check digit out. And transpositions are a very common mistake when you're typing things into a database, for example. And something like parity, if you transpose 2 bits, it's not going to notice, because the sum will still be the same. But using this weighted sum and going modulo 10, it catches those kinds of mistakes pretty nicely.
But if you had some whiteout or something, and you whited out a check digit and like change one of the numbers, like couldn't you, I mean in theory, couldn't you actually change what the barcode read as?
If you could actually change the barcode, but I think the way the bars match to numbers makes it difficult.
Okay.
I gotta say, sorry. What was
Go
it?
ahead.
I was gonna say, I used to work retail and people try to screw with UPCs all the time and it never works.
Yeah, they just don't
I've
stand.
never seen it work. I've seen people tamper with them, like,
Yeah.
it never works though, because it's sophisticated enough that it can
Yeah.
tell that you did something dumb. Like,
Kind of like if you write a check for $1,000, it's pretty easy to change that 1 into a 4, because our numbers aren't resistant to tampering like that, but you can design a set of digits that are resistant so that you can't just morph one into the other.
Well, digits are, I don't want to say linear, but a certain number of
If
bars
you really
per
gotta
bit
map
to
that,
one
you
number.
can
So, for
Yeah.
example, a 2 is going to look the exact same as the cheat code. There's a start and end,
Right.
but the 2 is going to look the same.
Right.
So it's not necessarily tamper resistant, it's more the people trying to tamper with the UPCs probably aren't aware of that.
You might be able to design it in a way, though, that forces it to, I don't know.
Yes, but is it?
I don't know. I would hope so.
I mean, you could do it like a QR code. There's nothing, you can't say, oh, that little piece of the QR code is an A or something like that.
Right, but if you have whiteout, yes, all bets are off. If you just want to add to it, I can see how you could make it so that additively you can't turn it into something else that's meaningful. For example, if you only had 1 bar and it was just based on position in there, there'd be no way to just add another bar because you have 2 bars in that cell. But if you're armed with whiteout, sure, you can white out the whole thing and stamp your own code.
That's actually more common.
Yeah.
I work retail today, and you'll more likely see people trying to switch the UPCs
Yeah.
than to change the UPCs.
Yeah,
Right.
usually like apparel.
Sticker on it.
Which that's much easier.
Yeah.
but then there's weird stuff where it might not ring up in your system then, and it's kind of a crapshoot.
Well, if you have 2 items, but yeah.
At which point, you then check the weights of the 2 items based
Yes.
on the stuff stored in the database. So it's
Or use
kind
your
of
tricorder and check the material. Which you can get on Kickstarter now, by the way.
Or read the screen.
So another version of this is ISBN. So this numbering code that's used on the back of printed textbooks, and it's a unique code for each book, each edition, each version of the book, and that's got check bits built into it also. It's a 10-digit code. You basically add up your digits, you multiply them by the position in the number, and you reduce it modulo 11. And that also catches transpositions.
Let's say 13 digit, 10 digit.
There's a variety of them. There's a 13-digit, there's a 10-digit, there's at least a third one.
yes.
But is the algorithm the same for all the different numbers?
I don't think so. And I don't think the 10-digit is very popular.
Yeah, they're all
Yeah, usually
distinct from one another.
Yeah, I usually see 15.
So number of digits 13, formerly 10. Wiki. Originally created in 1967 based upon a 9-digit code. So, but yeah, it has a check digit, and it's another weighted sum of the digits, and that's reduced modulo 11.
So you just download it, it's up in modular 11.
Yeah, multiplying by the position of the number. MD5 hashes, when you download a big file from the web, there's always a thing attached to it. It's an MD5 hash. It's another check, not a digit, but a check number. So that if you change something in the file that you're downloading and you generate the MD5 signature from that, you'll get a different number. And that protects you from downloading malicious code. I think I'm downloading a version of PuTTY, but it's actually been changed to have a virus inside. It won't generate the same code.
Only if the hash is distributed securely.
Yes.
But if,
Yes.
if you're on download.com, literally download.com, and you
Yeah.
download PuTTY and they give you the hash,
Right, you got no way of
that's
knowing.
not safe.
That's them saying that we're giving you.
That's actually worse, because then you're convinced it's safe, and
Yes.
you give it to all your friends.
SHA1 is similar?
The what? Yeah.
Heard that too.
All right. Hash functions. We'll talk about hashing in 222, but you'll see modular arithmetic coming up in that. I don't want to go through that right now. Let's talk about encryption. So encryption ciphers, codes, basically you're trying to find a way to convey information from one point to another without somebody who's unauthorized gaining access to that information. And a long time ago, people gave up on secure channels, giving your message in an envelope to a courier and saying, don't let anybody take this from you. It's not secure, right? If enough people are interested in it, they'll find a way to get that piece of paper out of the courier's hands. If somebody's really interested in knowing what you're transmitting, they will find a way to intercept that transmission. And most of our transmissions are going through the airwaves. Airwaves are public domain. Anybody can listen to them. Okay, so there's no security in the channel itself. So you encrypt the information. You make it so that if somebody sees what you're actually sending, they can't get the message out of it. So you scramble it up in some way, and only the person who's receiving it knows how to unscramble it. That's the theory. So one of the earliest ciphers, I want to send my secret message to someone to say hello. Add 1 to each letter, so this becomes I, F, M, M, P. And that's the message that I give to the courier. And they get jumped on the highway and they steal the message and it says, imp, I don't know what that means. And my message is secure. Okay, that's called the Caesar cipher. Presumably Caesar did this. And you add something more interesting than 1. You add 17 or something. And it gives you a message that looks like gibberish. And if you don't know this algorithm, you have no way to decode it. But of course, once people figure out, oh, Caesar encrypts things by adding some number to each letter, you could try all 26 possible values and find which one gives you something that makes sense. So that's a really easy cipher to crack. And it's also called a shift cipher. There's 2 problems with this. Well, there's 3 problems with this. 1, you can crack it by just exhaustively trying different combinations. 2, you can do a frequency analysis on this. Right? The letter E is the most common letter in the alphabet. So if you analyze this piece of text that you've been sent, you find that G is the most common letter in that. You can assume that E maps to G. And so if you subtract 2 from each letter, you're probably going to get back to the original text. And frequency analysis is a common method of attack. The 3rd problem is, once you know the algorithm, right, all bets are off. Actually, the 4th problem is, if you know how to encrypt this message, you know how to decrypt it. Right? You subtract 1 instead of adding 1. Which means that every person that I want to send a secret message to needs to have their own encryption key. I'm going to send you a message by adding 1. I'm going to send you a message by adding 7. Because if you happen to see the message I'm sending to somebody else and I'm just adding 1 to their message, you can decode it. So for each entity that you're sending that's sending information, you need a different encryption key. Otherwise, everybody can read everybody else's messages. And this is a key problem with something like doing commerce on the internet. We all want to place an order at Amazon. We're going to send our credit card number. Well, if the secret is just add some number to each digit, and I'm going to add 5, and you're going to add 5, and you're going to add 5, I can listen to the number that somebody is sending, subtract 5 from each digit, I got their credit card number. So the only way around would be like, okay, Nick, you're going to add 5, but you're going to add 17, and you're going to subtract 3, right? And then it would be secure, but that's not practical. You can't have everybody who wants to send you a credit card have their own secret password. So this works for simple cases, but it's not super secure. Another version is a transposition cipher. where we would take our message hello, and we'd break this into, say, groups of 3 letters, and we'd say, let's say 1 goes to 3, 2 goes to 1, 3 goes to 2. So we would say this first letter becomes the third, the second letter becomes the first, and the third letter becomes the second. And over here we'll just add a blank to the end, and the first letter will become the third, the second letter will become the first, and the third letter will become the second. So this becomes our message.
LOL.
LOL. And a frequency analysis won't help you here, but there's other ways to figure out what the magic transposition is, and once you figure out how you're transforming things, then it's pretty straightforward to crack. And you can figure out what your block size is by doing some statistical analysis on your text and find patterns that occur. So that's not terribly secure, but that's a different approach, is this transposition. And again, if you know how to encrypt, you also know how to decrypt. The decryption key is 3 goes to 1, 1 goes to 2, 2 goes to 3. So character 3 is the first, character 1 is the second, character 2 is the third. Break it up here, character 3 is the first, character 1 is the second, character 2 is the third. So if you know how to encrypt, you know how to decrypt, and vice versa. Well, we'll start with tomorrow. Public key encryption. So in public key encryption, I can tell the whole world how to encrypt a message to me, but nobody can decrypt it except me. So knowing how to encrypt will not give you any information about how to decrypt. So if I'm Amazon, I can say, here's the algorithm everybody's going to use to send me your credit card. And everybody knows that algorithm, and everybody can look at what you're actually sending me once it's been encrypted, but nobody knows how to decrypt those messages except me. Because the encryption and decryption keys are different. And you can't figure one out from the other. Here, we can figure that out from here. We can figure out the decryption here because we know the encryption. Public key encryption, total game changer. No way to tell how to decrypt just from knowing how to encrypt. So we'll talk about that tomorrow. And then we'll go back and we'll talk about functions, sums, and matrices. And then we'll go on to induction probably Wednesday.